Yeah. I guess we'll go ahead and get started. I think most of the stragglers have made their way in. I get the coveted last session of the day right before all the door prizes, so you guys are the few and the proud, right? Now, it's going to be important, with such a small crowd, it's going to be important to have this a little bit interactive. I don't intend on standing up here and speaking. Are we okay? You got me? Okay, cool. It's going to be important for it to be a little bit interactive, or it's going to be really boring. So I hope there's a few of you that don't mind me kind of using you as a point in the audience to maybe help me make a couple of my points. If you don't want to be that person, then just pretend it's like somebody is asking you to pray in Sunday school and just look at the floor, and then we'll be good, okay? So I want to talk to you a little bit today about machine learning and AI. Kind of the underlying theme, though, is the machines are really not out to get us. They're actually out to help us do our jobs more effectively. A little info about me. I'll leave that up for a minute or so in case you want to grab my email. If you have any questions, if you want any further clarification. I am not an expert on this topic. I am an avid researcher and interested enthusiast. But I'll be glad to share any of the things that I've learned. I'll be glad to share my slide deck with you too. I don't know if they're sharing the slides as a part of this or not, but send me an email. I'll be glad to send it to you. So who's used machine learning? Show of hands. Oh, that's way too few. You've probably all used machine learning. Have you ever been surprised when you posted a photo to Facebook and it said, would you like to tag so-and-so? Who's had that happen to them? You've used machine learning. Who's had Siri or Google now voice recognition? I mean, that's commonplace, right? You've used machine learning. Netflix suggestions. It's always anime and superheroes for me. Yes, I'm that kind of nerd. Spam filtering for your email. We don't even turn this on anymore, right? For most web-based email services, Outlook.com, Hotmail, Yahoo, it just works, right? Do you get as much spam as you used to? You don't. Machine learning. Yep, you've used it. So now by a show of hands, who's used machine learning? Almost everybody, right? Everybody's used machine learning. You know, you just didn't really label it as machine learning. So why the machines? The machines are faster. They have more memory over a longer period of time, and they can notice details that we cannot notice as humans. Who has done the wonderful job of being a security operations center analyst or an analyst for any sort of security stuff? It's not easy, right? Picking through a haystack, you got lots of data to look through. How do you weed through the mountains of logs? Well, everybody really kind of knows that we don't do a real good job of that. So let's see if the computers can help us a little bit. But in order to kind of set the context for how computers can help us do security-related tasks, I want to lead you through a couple of exercises so you kind of understand how machine learning works. And then I'll tell you about a couple of flavors of machine learning, and then we'll talk about a few use cases. We'll wrap it up and get you guys off to the door prizes. So my dad is a car aficionado. He was born in 1948. So he was about 8 years old when these really cool Chevy cars came out. He's a Chevy fan. And early on, I saw a lot of hot rods. I was born in 1971. So it was about 20 years. As I'm a young kid, I'm starting to see these cool cars. 57 Chevy. Who's seen one or can probably pick one out, right? And I asked my dad, what's the difference between 57 Chevy? Why is it so much more popular than the others? Well, he kind of started telling me these little differences in the car model. So as I show these, some of you that know these cars will be able to pick out which one is, there's three models here. One is a 55, one's a 56, and one's a 57. Anybody know what that is? Any guesses? 55, right in the back row, absolutely. Yeah, it's 55. Why? Tail fins aren't tall, and the chrome is flat on the side trim. You probably know this one, right? This is the popular one of the three, right? This 57. Why? tall fins, sharp angle here, and this wide dipping side trim, and then this wide panel right here. Very interesting features of these cars that are distinguishing, right? And then of course that leaves us with 56, right? These, the fin does not have a sharp angle, it's flat, more like the 55, but the side decals go down. Some fairly distinguishing features of these three cars. What if I looked at these three pictures and I told you, well, it's the 55 is the 55 because it's blue? Wouldn't make any sense, right? It's the wrong features. But it is a differentiator between the 55 and the 56 and the 57 models that I've put up here, right? These two are red, therefore we might conclude by looking at some features that they're the same. They also have silver trim. These two have the same wheels, similar front end. If you look at a 56 and a 57 front end, they look very similar, right? So your brains are now starting to think about features. How do we tell the differences between things? I'm going to lead you through another exercise that's a little more involved. What are these? So everybody gets to join in as I show these pictures. What is this? It's a chair. How do you know that's a chair? Somebody tell me. One thing that, it's what? 4 legs in the back. Okay, I'll buy that. Those are pretty good features. All right. What else makes this a chair? Just by looking at that. I mean, we know that chairs are things you sit in. It's flat.
Yeah, it's about flat and it's about yay high.
So it's somewhere between 18 and 24 inches is the horizontal surface. Okay, I'll buy that. That's a good feature. What else? It's human sized. It has a good form for its function. Sure, yeah. What else? Anything else? One user? Okay, I'll buy that. That'll make a little more sense when we talk about some other things here in just a minute. What is this? It's a chair, right? It meets the requirements, right? Seat height, butt size, 4 legs, it's got a back, horizontal surface. Meets all those features. What's this? Is this a chair? I'll call it a chair. It's almost just like the first one, right? Very similar features. Uh-oh, here's a different one. Is this a chair? What about this one? It's a bit different though, right? So think about the process as we're learning this, and we'll get to this, the next set of pictures that'll kind of throw you a little bit for a loop. These are all chairs, right? Should be blatantly obvious. I've given you an entire slide full of chair pictures. But what did we do? We came up with distinguishing features for what makes a chair. Now, oh, is that a chair? Okay, we'll call it a chair. So we knew this because we have processed a lot of images of chairs through our pattern recognizers, our brains, and we are given features. But when I mean, most of us don't remember when we didn't know what a chair was, right? So we know what chairs are just intuitively because we've processed a lot of images. What's that? It's what? It's got 4 legs. It's got the right height. It's got a horizontal surface. So what feature are we missing that distinguishes this as a stool and not a chair? It's got a back, right? So we know this is a stool. What is this? It does, okay. We've had a pattern recognition failure right here. We've got a spaceship up here, right? What is this? This is a stool. And that? Coffee. That's a small coffee. Somebody's got a small living room. So how are they different from chairs, right? No back. Okay. Chair or stool? It's got a bit of a back. What other things could I use to determine whether or not this is a chair or a stool, other than the features that we've already talked about? Height of the back. We could go with that. Sure, I'll buy that. What else? Height of the legs is higher than what we would normally consider a chair to be, right? What about this one? Oh dear. This is very chair-y. Yeah, I'm going to call this a chair. It meets all my chair requirements. It's got a back. It's got a seat. Oh wait, one of the features wasn't right. This one has a feature that's off from the ones we talked about chairs. Seat height, right? Features are different. So therefore it is not a chair. Probably call it a stool. Or a chair stool. Maybe it's a new thing altogether. What is that? This one doesn't even have 4 legs. It's not a chair. Chairs have 4 legs. This is missing key features to define it as a chair. And it's art. It's art, okay. How do we know? How do we determine chair or stool? If I give you 2 categories, and that's what you have to choose from, right? These are the answers that I want you to come to. Is it a chair or is it a stool? Which one are you going to give me? Chair? Okay. Who would say it's a stool? Any brave souls? I'll stand alone and call it a stool. Because it doesn't meet a lot of the feature requirements for either one. So it's kind of in this indeterminate state. I'm not sure. All right, I'll agree with you. It's a chair. What's this one? Chair? Stool? I hear a lot of chair. Do I hear any votes for stool? Got a brave soul in the back. Stool? Why? What's the thing that differentiates it, makes it a stool? What did we learn in our categorization? What? It's taller. Seat size is too high to be a chair. It's not between 18 and 24 inches. This one's tall. Now you can't really tell that unless you actually see it and measure it, but I tried to get these at least in some general ratio where they look similar. So this, call it what? A bar chair? But that's not one of the 2 answers I gave you. We got to either call it a stool or a chair. All right. Now let's look at some really, really, really interesting examples. What is that? It's quite a bit different, right, than what we've looked at. But we would still be able to call it a chair based on the features that we had, right? It's got a butt-sized horizontal surface, 4 legs, even though they're short. It's got a back, seat height. I'm going to call it a chair. What about this one? No legs. It's not a chair. But it also doesn't meet my requirements for a stool. So what we have to do now is we have to, since this one doesn't meet either set of features, now we've got more features that we have to take into consideration to make a determination between whether something is a stool or a chair. This is obviously a chair, right? But why? 4 points of contact. Okay, so we're going to now revise our definition of chair. Instead of 4 legs, it's got 4 points of contact. But that really messes up the little blue round one, because it had 6 points of contact in that office chair. So we don't have to come to an exact determination for what these features are, but what you know now is we've got a new thing that's different. We know it's a chair. How do we define some features around what it means to call this a chair? So you're starting to understand the difficulties in machine learning. Because we know these things intuitively. Computers don't. What about that one? Holy moly. That's a chair and an ottoman, right? We know that. There is a stool. It's a stool and a chair, right? Ugh. What about that one? No Game of Thrones fans in the house? Okay. I expected a little more response from some of you all. Okay, one last thing. What is this? Chair or stool? Stool? It's too low. Huh? Too wide. It's got room for 2 or 3 butts on it. bench, coffee table, it's a new thing. So again, now we have to adjust. If I want you to make a determination of whether this is a stool or a chair, I don't give you the possibility of calling it a coffee table. What are we going to call it? I'm going to call it a stool, and I'm going to rewrite my features to include the parameters for this particular object, right? This is exactly how machine learning works. Specifically, this flavor of machine learning is called supervised machine learning, where we have a set of desired outcomes that we would like for the machine to determine for us. Chair or stool. Now, in order to get a machine to make that determination about those images, we have to feed lots of images into it. Thousands, millions of images into a computer that can do image recognition and tell it these are all chairs. And then we feed millions more images into it that are stools. And then let our algorithms run. We get some really smart programmers to write some algorithms for us to make those two determinations, to start to look at all of those images and determine, is it 4 points of contact or is it just 4 legs? Can I have a chair that has a round bottom? Can I have a chair with no legs? Those sorts of things are things that our algorithms have to be written to be able to kind of understand as far as image processing goes, so that we can do machine learning to make a determination of whether or not something is a chair or not, or, unfortunately, maybe we don't know, indeterminate. Sometimes that's what we end up with. But tons of data go in. We feed the machine. This is this body of stuff is this, and then we hope that the machine is able, after some running of the algorithm, to come up with a model that says, here are the features of these objects that you fed me that will determine whether or not it is in class A or whether it is in class B, whether it is a chair or whether it is a stool. Unsupervised is a little bit different. So the two examples that I've just given you is supervised learning. We have desired outcomes. Unsupervised looks at the data to determine baseline. What is the normal state? What are patterns that are within the data itself without actually making determinations as far as what the patterns mean? But this is a pattern in this data that I see, whether it's a pattern in the images, whether it's the fact that we make a determination that it's not the color red that makes the differentiation between the years of a car model, but it's the trim features, right, that make the differences in the car models. Unsupervised might be able to take a look at that and say, okay, I see this pattern that all of these objects are all red. It doesn't make a determination. It just says all of these are red. Every object you fed me is red. When I feed it a blue object, what does it do? This is not normal. And if we do that over a long period of time with a lot of data, and we write our model such that it can look at all of the minute details that might be in the images or files or network traffic or server logs or firewall logs that we send to the machine, it can determine what normal is and do a much better job at detecting anomalies than we can. We can't look at that, a huge set of data over 6 months, and parse it all in our head and be able to look at any given 5-minute window and say, is this normal or not? We just can't do that. Our brains can't do it. But computers are really good at this sort of stuff, right? So this is what unsupervised learning does. Any questions on that or points of clarification? So we look for baseline normal behavior, and once we know what the structure looks like and what it should look like, any changes that we can observe really then become things that we probably ought to pay attention to. So, what are our use cases? So this is a security conference, right? You didn't just come to learn about machine learning. Antivirus. What kind of learning are we doing with antivirus? First, we should probably talk about what question are we trying to answer with antivirus? Anybody want? Malicious or benign, right? So in that case, then we have two desired outcomes. Therefore, what kind of machine learning do we use for that? Supervised. Supervised machine learning. Turns out, we'll talk about it here in a second. Network analytics. Feed all of your network data. We're now kind of at a point where with the compute capacity that we can have in the cloud, with the storage capacity that we have in the cloud and the cost thereof, we could conceivably store a lot of network data, a lot of logs in the cloud, and have enough compute capacity and enough, basically compute capacity, to actually analyze all that stuff, right? All we really need is somebody smart to write the algorithm to look at it for us and determine what normal looks like over a long period of time. Because why can't we determine normal? We can't think in the time scales. It's a matter of scale, right? The computers can just do this way better than we can. Machine behavior. What sorts of things do we look at in machine behavior? What are the things that we care about that determine normal versus not normal on a computer? File accesses, processes, network accesses. And there's all sorts of stuff that we can look at on machines, and there's tools that let us do that. The key is to get that information in one place so we can do analytics on it. And again, it's really all about time and the amount of data that we can take a look at. Identity. What are the things that determine who you are on the computer? That it's you and not me. What things do we use today to determine it's you and not me? Username, passwords. Okay, common. What else? Biometrics. What else? Tokens, something I have, right? What else? Oh, now we're starting to move in some more interesting stuff. When I log into the computer, okay, how could that determine? Chris normally doesn't log in until after 8 a.m. That's been a proven pattern over years. I log in before 8 a.m. Is that normal? That is not normal. I should probably pay attention to that. Should I pay attention to all of the other normal activities? Maybe not. What else? Do you know the patterns in the ways that you wake your machine up with your mouse and the keys that your fingers hit first on the keyboard and how you type in patterns? Just the timing between the letters that you type and the way that you use words in typing can be used to identify you uniquely. With 100% certainty? No. But if you combine that with all of these other things, we could potentially feed that into a machine to say, is the person using this computer based on all of the stuff that we know about how this person is using the computer, is it still Chris or is it somebody else? This is probably the edgiest use case right now because we don't have a good way to do this real time, to capture all of that data real time and do user-based real time. But we do there are actually some products out in the space, and I'll talk a little bit more about them here in just a second. So let's dive a little bit into these use cases. Antivirus, right? A lot of samples. Do we know of products that do this today? Who knows of one? They told me not to talk about products, but that didn't mean I couldn't get you to talk about products. Huh? There's VirusTotal. There's some endpoint solutions that do this. Silence, that's one, right? They were out here, right? Who else does this? A couple of other vendors in the space, but we're starting to see really some merging of functions, and most of the endpoint security vendors are starting to see that machine learning makes a ton of sense. And if you're not doing machine learning, you're not doing your job as far as antivirus goes. A lot of organizations are finding high levels of efficacy in their antivirus software by using next-gen antivirus products that are based on machine learning and artificial intelligence. But they have to have smart people to write the algorithms. They have to have a lot of samples, like petabytes of file samples to look at the file features. How are the files signed? What does the machine language look like? I mean, there's all sorts of things that we can look at in files that aren't just this pattern in the file means it's malicious, right? Because that's traditional antivirus. This string of bits means this file is malicious, and we can never be proactive. We're only ever reactive with traditional antivirus. With machine learning, we can actually be proactive. Files with these features are malicious, and we can make that determination with a great degree of certainty because we've fed a huge amount of data into it and said, here's millions of malicious files, go work on this. Here's millions of benign files that we know are good. And then we start to feed it unknown samples that we don't know whether they're malicious or benign. And then we can measure how effective our algorithms are, improve the algorithms, rerun. And over a period of months and years, we can come to a solution that's really actually quite effective, and they actually have these in the space. Some of them we've already mentioned. But you need lots of storage and compute capacity to run the algorithms. But the cool thing is, once the algorithms have run and you've determined what the features are that you care about, you can come up with a much smaller subset of those that can actually run on an agent. You don't need to actually run the AI and the machine learning on the agent. You just run a very small model of the larger corpus of learning that the machine has already done. So you don't have to have a cloud on your premise in order to do machine learning based antivirus. Run the algorithm, feed new samples in, generate a smaller model that includes the pertinent features, and that's what we care about. Several mature commercially implemented examples. If you want those examples, we'll talk when I'm not on the mic. All right, network and machine behavior. So I kind of lump these two together because they're very similar. We capture all the network activity, we capture all of the machine behavior, all of it. Feed it up into one place, run the machine. This can be terabytes a day for a decent sized network. You probably don't have these resources on site, right? This is something that somebody else is probably going to have to do on your behalf. And then you determine a baseline, because that's where, and so we've moved into what kind of machine learning here. When I say the word baseline, it's a different kind, right? So we're not determining good or bad, we're determining normal or not normal, right? So now we've moved into doing unsupervised machine learning. So we make a baseline and we look for deviations in the baseline. What is normal? Does this machine ever access this resource? Does it ever access this website? Does it ever access this registry entry? 5, thank you. So these tools, great, thank you. These tools are maturing still. Not as mature probably as machine learning based antivirus solutions, but cool thing is most of them, the commercially available products that are machine learning based antivirus are looking at this space too. So where they've been successful with getting machines to determine whether a file is malicious or benign, they're starting to recognize that we need to play in this space, and you can use those same data scientists that run those algorithms in the same storage and compute capacity that you had to run against all those benign and malicious files to do these same sorts of calculations to determine what's normal and what's not. And then tune a set of tools that can look at very specific features instead of all of the features. Look at the ones that are actually important in determining normal versus not normal. And then you can run that actually in a much smaller agent on actual PCs that don't have the same compute capacity that your large machine does. It's probably in the cloud. So identity is a little tougher. We have to measure continual usage of the computer, measure the time. I mean, the things I mentioned before, the more sensors that you have on a computer, the better you're able to measure things that are important to determining user identity. Has anybody used the Windows facial recognition for authentication? Like it? So who's used it? Really? Has nobody even tested this? I'm able to fairly consistently get my test machines to look to determine that it's me and log me in when I'm wearing a hat, when I'm wearing glasses, take my glasses off, when I've shaved my beard off. It's able to make those determinations. It's a little bit better now because they're actually using a special IR camera to look at heat patterns so that you can't just shove a picture of me up in front of the camera to get it to authenticate you as me, which was the old way of kind of fooling those sort of facial recognition algorithms. The more sensors you have, the more you can determine about who a user is, right? And we should use them. They're getting more accurate. And the combination of multiple sensors instead of the reliance on one, like fingerprint. I mean, how long have we been talking about using fingerprint recognition for authentication? It's got problems, right? Not as reliable. Sometimes it won't get you logged in right. But if you use the combination of all those sort of things to say, this person looks 99% like Chris, yeah, that's great. So the more sensors that we get, the more we can measure. And the more things that we can think about that are actually able to determine not just specific things that are who I am, my fingerprint, my face, but also my behavior. As we combine all of those, we can feed those up into a machine and determine what is normal for me is not, If we can determine what's normal for me, and then we can look at anomalies in that behavior to determine, is this still Chris or is it somebody else? And then if we're really picky, we can say, what do I do? Is this just Chris behaving differently, typing differently? Is he sick? Is he drunk? Is he heavily medicated for some reason? Or is this really actually another person? That's what we have to, I think, where we're still starting to see some of the maturity in this area. And there's actually some commercial products that do this sort of stuff. The challenge is, can we make those models small enough and read that data quick enough and let the machine make a determination quick enough that we can do this in real time? Because I can't wait months to develop a math model based on my behavior just so I can log into my machine, right? But this space is maturing even though there aren't a whole lot of commercially available products. It's an area of interest for a lot of people, and if you talk to folks that are doing, vendors that are doing any sort of machine learning in the commercial space, they recognize that continual identity is a problem that machines will solve for us at some point. It's a matter of when we get there, getting the models written right, and then finding a way to implement it on endpoints. So will we get rid of usernames and passwords? Maybe. So, in conclusion, machines are better than us at this stuff. Way better than us at this stuff. The problem that we have is it's kind of hard for us to get our heads around how the machines are doing this work. So I kind of put this talk together to kind of give that high-level overview of how machines do, how we do learning, and how that kind of translates to machine learning. Because I've actually sat around the table with folks that said, I get this next generation antivirus stuff. It seems to make sense, but what you're telling me is I have to trust that the machine is making a correct determination. I really want to know how the machine made the determination. And with traditional antivirus products, I can do that, right? I can look at the signature and I can say if it has these bits in the file, it is a virus. It's malicious. If it doesn't have those, then it's not that. And if I check all of the known samples for malicious software and I have a signature for those, then I can rest assured that at least of the things that we know about, this is not one of those. So what assumption do we make? It's benign if it doesn't match any malicious patterns. We can get our heads around how that works. That's an easy process, and I can look at it and actually know what the bits are. But you can't possibly know the corpus of data and all of the features that went into training a math model to then narrow that down to a certain set of features that say this is what is determining whether something is malicious or not. It's too much data over too much time for us to get our heads around. So we just have to trust the machines, like it or not, if we're going to rely on the intelligence that they can bring to bear, the computing capacity they can bring to bear, the storage capacity they can bring to bear to solve some of these sorts of problems. And, oh, by the way, in addition to machine learning, we can also use artificial intelligence algorithms of various sorts to improve the machine's abilities to learn, to supplement the machine's abilities to learn, because these are two different things. Artificial intelligence does not equal machine learning. They're two separate things. All right. I think I have a little bit of time for questions. Any questions? Yes?
So given this and three big areas of what we do in security, where should people be investing their time to stay relevant?
Good question. I think one of the things that I have found, and this is of particular interest to me, is to kind of understand how this stuff works. I think that's important. And then to stay relevant is to, wow, tough question. I'm not really sure how to answer that one. If the machines take my job, what do I do, right? I think we can move into things that really require more neurons than just the rote stuff that we can get computers to do for us. I think for a long time we've kind of assumed that we need a full-time staff of 4 or 5 people to be looking at logs all day long. Well, now we have a solution to that. Machines can do that for us and we can trust them to do it. We should let them do it for us and then we can move on to higher level things. What those are, I'm not sure. I'm going to work on my 74 Dodge Dart. That's what I'm going to do. Any other questions? Yes?
What do you think we're not smart enough to know whether they're supposed to check, right?
No, we are, because I've had 45 years of training over a lifetime of experiences and probably millions of chairs that I've seen to know what a chair is. Yeah. We don't have that amount of time to think about the next malicious variant of viruses that are coming out, though. I don't have 45 years to train you to figure out what that looks like. And it wouldn't be worth my time when I can get a computer to do it like that. So the things that are hard for us to learn, we can offload that to computers, or not. Yes?
Okay, as far as like machine learning, you can say it's either this or it's not that.
Mm-hmm.
Is there like line in the middle?
Well, so that's why I stepped you through those examples of what is this, right? It's things that do match one or the other. That's where we have to retrain our models to determine. Because remember, in supervised learning, we have a set of outcomes, whether it's in the case of antivirus, right? It's either malicious or benign. Well, most folks have also kind of come to understand that there's kind of this middle thing that's gray, right? Yep. And refine our models to understand new features, and we incorporate new features so that we can make better determinations. Because usually it's not a binary sort of thing. It's not a 0 or a 1. This is good or this is bad. It is, this is mostly bad, this is mostly good, and there's a whole lot of stuff in the middle. And that line has to move, and we have to train our models to hopefully sort those things much further. Kind of like the opposite of a bell curve, I would guess. That's not very mathematical of me. I should probably not talk where I... Pardon? Sure. Yep, we do. Any other questions? Yes?
This is kind of silly in a way.
Okay, I'll be glad to give you a silly answer.
There's that online debate if this is a hot dog or sandwich.
Is a hot dog? Yeah.
It got to the point where even people couldn't really determine whether or not
Mhm.
it was a hot dog or sandwich, right? So what happens with, for example, with machine learning? You know, and we ask, hey, which ones are hot dogs, which ones are sandwiches, right? Is the issue with the underlying definition, or can they come up with a answer to that? And if they do, how do we know it's valid?
Yeah, so in machine learning, if we're going to have an answer questions for us, we have to have determinate answers. We can't have indeterminate answers. Or machine learning can't really do it, because I can't then feed it a corpus of stuff. For example, if I have known malicious and known benign files, and I feed millions of files into my machine and have it crank on that stuff to figure out what's what, I can't also have underlying this indeterminate state in the middle where it's not and feed it a bunch of files that I don't know anything about. You don't do that till you train the machine to know what's what. It knows these are malicious, I know these are malicious, go chew on these. These are benign, I know they're benign, go chew on these. Now you have to hope that you got that right when you fed it to the machine, or the machine will make bad determinations. But given that, the machine is able to sort that stuff out to where you can have a reasonable degree, a fairly broad boundary where you don't have any indeterminate answers in the middle. It's all about the algorithms and the math models that we use to do that, really. Yes?
Okay, so typically, human doesn't understand something else. We'll go and ask somebody else, with a machine learning, do they program it to program it that's learning, ask questions?
So what we do is we use the feedback loops, and so specifically when we talk about supervised learning, we say these are good, these are bad, and then when the computer's unable to make a determination we've told it these are good and these are bad, then we feed it something unknown, and it's not able to make a determination, then we have to come in, and that's why they call it supervised learning, and help it make a determination whether this is good or bad, help guide it. And that way it can relearn. So that's why they call that supervised learning. It requires some intervention of a higher power to guide the process. Whereas unsupervised is just saying, I'm not making any determinations here, I'm just telling you what I see. This is all what I would consider to be normal, and now something has happened that's not normal. That's unsupervised learning. We have a lot of undeterminate answers there because we're not really making any conclusions other than a baseline. Yes? Mm-hmm.
I would actually argue that your chair is a broader category than your stool or your chair.
Okay. So that would be assumptions that we would feed into our learning model to say that we know there's this other state of things, right?
So, thought process in machine learning, that goes only as good as the algorithms.
Yep, as the algorithms and the corpus of data that you feed it.
Correct. And so, one of the things, so if you guys know there's a huge data science community in Kansas City, they are discussing some stuff.
Mm-hmm.
And I have a unique background because I have a meteorology background. We do not ignore outliers. For the most part. Or we look at outliers and we just check them. Whereas data scientists are like, oh, that was an outlier. Well,
No, you can't just discard that stuff. Yeah.
I just don't like data when you got that out.
Right, right. Yeah, I think so, but I think if we look at the outcomes that we're trying to determine specifically with these sorts of tools, I mean, the one that's very applicable and that has had a high degree of efficacy is antivirus, malicious or benign. We've done a really good job collectively of solving that problem with machine learning, even in encompassing all the outliers, because the outliers should become input into the development of the algorithms and into the next corpus of data that we use to train the machine. So it's not a set it and forget it where you run it once, then now I know how to make these determinations, because new stuff comes, right? And then we have to make more determinations and rerun the algorithms and relearn. That's how we work. Yep. All right, I think I'm out of time. Thank you.